All right, so welcome to Wednesday's lecture, the last lecture of the week. We left off yesterday with finishing one-dimensional and two-dimensional dynamics, but there's a small caveat there. So let me motivate, I guess, today's topic. So we talked about what caused motion, which is a force. And we started simple. We started with talking about forces in one dimension, just to kind of get us familiar with what a free body diagram is and what F net equals ma is. And then we expanded that analysis into two-dimensional motion. And we said, well, you know, objects in real life, they don't just move left, right. You know, they move left, right, forward, back. You know, there's sort of two dimensions of motion there. And well, in fact, in real life, there are three, but, you know, baby steps. And what we learned yesterday when we did some examples was if you have a two-dimensional forces question, you really don't do anything any differently. It's just like with the projectile motion, you know, with kinematics. With forces, you perform two independent one-dimensional motion analyses, right? So you do F net x equals mass times acceleration in the x direction, and then you do like F net y equals mass times acceleration in the y direction. And you know, that's assuming your coordinate system is x and y. There were some questions we did where we rotated our coordinate system because there were more vectors that were in a rotated coordinate system than there were in a normal xy coordinate system. So it made more sense to rotate the coordinate system in that sense. But all of that analysis is good and all of that background is good, and we're feeling really good about ourselves that we can now, you know, analyze a lot of different types of motion. But there's still a piece of the puzzle we're missing. And really what I want to point out here is when we did F net equals ma, that acceleration was linear, right? It was, or I should say tangential. You could decompose it into, you know, acceleration x, acceleration y. What if the object isn't really moving in a nice, neat, linear way? For instance, like, what if the object is moving in a circle? And if it is moving in a circle, can we analyze the motion the same old way we've done before? And I mean, before even analyzing it, the answer might very well be yes. The answer might be, yeah, we don't have to do anything different. We just decompose it into components. Or the answer might not be as simple. Point being is it's a special scenario in which we have to sort of think about ahead of time first before we just move on and say we know everything about forces and motion. So without further ado, of course, my program here is frozen. Oh, there we go. There we go. So let's talk about the acceleration that an object experiences while it is undergoing circular motion. So first of all, what is circular motion? Circular motion is quite simply an object that is traveling, like the path, the trajectory of the object is physically circular. And there are different types of circular motion. Circular motion, just as a term, circular motion is just a generic term that says, you know, anything that's moving in a circle. In this class, in first year physics, we typically only talk about something called uniform circular motion. And the qualifier in front, the word uniform circular motion, means that the speed of the object is constant as it travels in this circular path. Now, I mean, let's think about a non-example. So like, you know, in driver's ed school, maybe you're 16 when you take driver's ed. When you're turning the car, driver's ed school teaches you to, you know, slow down into the turn. And then when you're halfway through the turn, they tell you to accelerate out of the turn. That would be a situation in which your car is in the middle of going through uniform circular motion. Sure, it doesn't complete a full circle, but there is a moment in time when the car is traveling in circular motion. It just doesn't necessarily complete the full circle. But during your turn, because the driver instructor told you to do this, you're slowing down into the turn, so your speed is constantly decreasing while turning. And then your driver's ed teaches you to accelerate out of the turn. So then, you know, halfway through and on your way out, you're accelerating, so your speed is increasing. That is an example of just plain old circular motion, not an example of uniform circular motion. Uniform circular motion, the object while turning has to be at the same velocity, or I should say the same speed, the same magnitude of velocity everywhere throughout the circle. That's important, and that's actually kind of dangerous when you're driving a car. I mean, you try to turn your car around a corner without changing your speed at all throughout that turn. It can be pretty dangerous. So this is this analysis is perhaps a little bit idealized for an academic setting, but it is definitely a stepping stone to analyzing real life and to kind of understand the world around us in real life. For those of you who have been to like an amusement park or something, you will have experienced circular motion if you go on like a spinny ride, whether it be like the teacups or the tilt-a-whirl, or I think at Wonderland, if you live in the GTA, they have a ride there called Nightmares. That's what the comic here is calling the Gravitron. Okay, so let's take a look at an arbitrary object traveling in uniform circular motion. So this might consist of an object like a ball attached to a string, and you know, maybe you're whipping the string above over your head. So you know, you're the one driving this motion with your arm, and this object is traveling in a circle. So we can sort of take a snapshot in time. When the object is at the top here, the velocity, the instantaneous velocity of that object is going to be pointing directly to the right, because you know the object will be coming up this way, and at that one very specific moment in time, instantaneous, the velocity will be traveling directly that way. And then maybe a few moments later, when the ball has, you know, reached down here, the instantaneous velocity of the ball at that moment in time will be tangent to the circle. And hopefully we all know how to draw a tangent line from grade 12 calculus and vectors, you know, even first year calculus. First year calculus may have been a while ago for some of you, but it's not a big deal. I mean, hopefully we all remember what a tangent line is. So we can visualize sort of two different locations on this path. And our question really is, what kind of acceleration is this experiencing? You must realize that, you know, when you study kinematics, acceleration is really where it all starts. And when you do dynamics, F net equals ma, acceleration is the thing in F net equals ma. So really, acceleration is the quantity we're interested in. So one of the kinematics formulas that we know is that the average acceleration, a average, or you know, another notation is using the sort of less than and greater than signs. A average is given by velocity 2 minus velocity 1 over t, or another way to write that is delta v over delta t. And it just occurs to me, I'm still drawing in red. Let's go to black. So this is just an equation. We can actually just vectorially add, or I guess in this case subtract, these values. So let's see here. There's vector v1. There's vector v2. So let's see here. It's going to be v2. Let me label this. This is going to be v2 plus negative v1 plus negative v1, which means we take v1, and we flip the head and the tail. So this is going to be negative vector v1, and then we add them. Oops. This is delta v. That's delta v. So we see that, and then you just divide by time to get acceleration. Now time's a scalar, so you know, something like the acceleration vector, the average acceleration vector, will look something like this. And that's the average acceleration vector between this position and this position. So we see here that the acceleration vector is actually sort of inwards. And this is using an analysis of just two arbitrary locations. You'll see if you choose locations closer to one another, or even if you prefer, we can choose, like a 90-degree angle. You'll see that the average acceleration vector is actually perfectly at a 45-degree angle inwards this way. And that's average acceleration, of course. It's really difficult dealing with averages. So if you want instantaneous acceleration, you obviously have to choose a point. So let's say the ball is now here, which is just, a delta t forward in time, or a dt forward in time. So the velocity vector would just be down a little bit this way. And then you see that delta v is straight down. So you see, actually, if you transform your analysis away from averages into instantaneous values, you start getting instantaneous accelerations that are actually perpendicular to the velocity. And they're always pointed radially inward. So the acceleration of an object in uniform circular motion is always pointing radially inward. Okay. Now, in terms of formula, the question is, what's the magnitude of this acceleration? And there's a well, it's not complicated. There's a tedious derivation of the formula in the book. Usually I do like to outline kind of where equations come from, especially if the sort of detail of where the equation comes from can provide some insight into the formula. However, you're gonna have to trust me here. The derivation of the formula for the circular acceleration is just tedious. There's really no physical insight that you can gain from the derivation. So I've left the derivation out, and I'm just gonna tell you the formula. So the main formula is that the centripetal acceleration is equal to the speed squared divided by the radius. And the derivation aside, let's think about the intuition behind the formula first. So picture yourself in a car turning a corner. I know I've already established that that's not necessarily a uniform circular motion, but over a very small time frame, over a half a millisecond or a couple milliseconds, whatever, your car is probably traveling at the same speed over a few milliseconds. So this is sort of analogous here. Let's think of the intuition behind this. Acceleration, you can feel acceleration. When your car starts from a red light into a green light, you get thrown back in your seat. Like your body can feel acceleration. It can't necessarily feel speed, but your body and your brain have a sense of how to feel acceleration. So let's think about this. If you take a curve, let's say the curve has a certain radius r. Your curve here has a certain radius r. If you take the curve pretty quickly with a certain speed v, and you just wrench your steering wheel and turn your car, your body is going to get thrown to the side of the car pretty viciously. And that's obviously not very safe. So what people tend to do is they slow down before turning. So they reduce their speed. Now, if they reduce their speed, the R is still the same, obviously. It's not like they change the radius of the turn. They've just reduced their speed. So if they reduce their speed and keep r the same, what you're doing is you're reducing the amount of acceleration required to turn that car or to turn that object. So if you reduce the acceleration needed, then if you were in a car traveling slower turning that corner, you wouldn't feel as big of an acceleration, which is why people slow down before turning a corner in a car, because that way you're not thrown to one side of the car. The other thing is, let's say you are driving fast, like me, I often drive too fast. If you kind of refuse to slow down, or just don't slow down for whatever reason, another way to sort of reduce the acceleration felt on that object is to take a wider turn. So, if you're turning, let's say you're turning right onto a side street, the ideal way to do that is to slow down, turn your car so it can safely directly turn into the right-hand lane on the side street. However, for those of us who drive, I'm sure you're aware that, if you don't slow down the car enough, sometimes you let your steering wheel go just a little bit so your car flares out and makes a slightly wider turn, and your car might actually cross the yellow line into the other side of the road, as long as there's no other cars around. And the reason why your brain intuitively does that is because you're increasing the denominator, you're increasing r, and thus reducing the required acceleration, making it easier to pull the car around a corner. So if it's a busy street, you have no choice but to slow down. But if it's if there's no one around and you want to save on gas or something, or you want to save your brakes, you could actually get away with maybe not slowing down as much and then just taking a slightly wider turn. So that's what that equation is saying, is that the acceleration required to pull the object around in a circle is proportional to the square of the velocity, and it's inversely proportional to the radius. So the other thing I want to mention is the sensitivity. Notice here that it's v squared, which means a small increase in speed will actually make a pretty big increase in required acceleration. So if you double the speed, you quadruple, 2 squared, quadruple the acceleration, versus something like r. If it's just inversely proportional to r, then that means if you double the radius, you only have the required acceleration. So the acceleration is more sensitive to speed than it is distance or radius. Now, another, I'm going to need to insert some space here. There are other sort of formulas that we can use depending on what variables we have and what variables we're asked for. So if you actually look, let me change my color here to black. If you actually look at a circle, we know the circumference of the circle is going to be 2 pi r. And if we have the object that we know is traveling in the circle, then we can say that the distance traveled is 2 pi r for one complete circle. And the time it takes, t, to complete one full rotation of a circle is actually called the period. And the whole premise is, if uniform, then we know we have a constant speed. So we can actually use the equation v equals d over t, and we know the distance is equal to 2 pi r. Oops, not t. Oh yeah, this is t. And the time is capital T for the period. It's the period of rotation. So we can actually swap out my speed in the above equation, v squared over r. Well, v is going to be 2 pi r over t. So this is going to be 4 pi r squared over period squared r. And then, using our math skills, we can do a little bit of simplification. And then another formula for the centripetal acceleration is 4 pi r over period squared, which is what we see right there. And another rearrangement, again, depending what kind of quantities we have versus what other quantities we need, another rearrangement is, let me just change colors for this. We also know that period is inversely proportional. Well, not just inversely proportional, it's the inverse of frequency. So, you know, if the period is 2 seconds, then my frequency is 1/2. I complete half a cycle per second. Using this, I could easily just swap out my period and say my centripetal acceleration is 4 pi r times f squared instead of 4 pi r over period squared. And that is where that equation comes from. So really, it's not like you have to know 3 equations. You really only have to know one of them, right? It's v squared over r. Just keep telling yourself v squared over r, v squared over r, v squared over r. If you do happen to need the other two, really it's not hard. The other two just come from the simple equation v equals d over t. And you can always derive them if you need them. Okay, so where does that leave us? We have now figured out that we can't just simply forge ahead with Newton's laws, F net equals ma, as if nothing's different, right? We've figured out that an object traveling in circular motion, the acceleration it feels is inherently different than when it's traveling in a straight line, like in linear motion. So now that we've quantified this, we have a formula for the acceleration. Now what do we do? And this is the big difference, actually, between physicists and literally everybody else. I'm going to specifically poke fun at the chemists and the biologists here. Though there's a little comic here on the screen, which is kind of funny. So this is from a website called XKCD. And I'll just read you the comment because it's kind of pertinent to what I'm trying to say. So first panel, how do you like my centrifuge, Mr. Bond? Presumably, if you're a chemist, you know what a centrifuge is. When I throw the lever, you will feel centrifugal force crush every bone in your body. If you don't know, Mr. Bond is James Bond 007. That's the joke. Second panel, you mean centripetal force. There's no such thing as centrifugal force. And then the evil villain, a laughable claim, Mr. Bond, perpetuated by overzealous teachers of science. Simply construct Newton's laws in a rotating system, and you will see centrifugal force term appear plain as day. And then James Bond on the centrifuge. Oh, come now. You really expect me to do a coordinate transformation in my head while strapped to a centrifuge? No, Mr. Bond, I expect you to die. Little funny joke. But this illustrates a point, actually, that in other branches of science, like chemistry and biology, they use the term centrifugal force. And yes, maybe, perhaps, this is perpetuated by overzealous teachers of physics, but there really is no such thing as centrifugal force. A centrifuge is used because when you spin a substance, a liquid substance, really fast, heavier particulates within the substance are going to, quote unquote, be pushed outwards. And that is what non-scientists describe as centrifugal force. People like chemists and biologists will say a centrifugal force is the outward push felt when an object is traveling in a circle. And again, science is an experimental physics. I can understand why Greeks messed up what force and motion was. You know, Greeks thought constant force was constant velocity because that's what they observed. And chemists and biologists, they observe when something is rotating, it appears, it feels as though that object is being pushed outwards. You know, when your car turns a corner, it feels like you're being pushed toward the outside of the turn, right? So if your car turns right, your body goes left. Your body feels as though there's a force pushing it to the left. That's what everyone else describes as centrifugal force. But you have to understand Newton's first law is inertia. A body in motion wants to stay in motion. So, you know, if you're going straight, actually, I'll just draw this here. If you're going straight and the car turns to the right, then Newton's first law says your body is in the middle of going straight. Inertia. Your body would want to remain going straight. So what's actually happening here is there's no outward force on your body. What's happening is you're going straight while the car underneath you is turning right. So what's actually happening here is the left side of the car is actually going to the right, and it will continue going to the right until your shoulder or your body hits the left side of the car. And it is only when the left side of the car hits your body that you yourself will actually start following the path of the car. So there is no outward force at all. The outward force that you know, chemists and biologists are describing is actually inertia. It's the law of inertia. And what's actually happening in actuality, in physically, is there's an inward force. There's a normal force from the side of your car pushing on your body inwards toward the right. And we know that the acceleration has to be inwards, so we know there has to be a net force inwards, not outwards. So there is actually no such thing as centrifugal force. It's centripetal force, and it's an inward force. So yes, you can call it pedantic, you can say I'm an overzealous physics teacher all you want, but we are in a physics class and we're here to learn how the world around us actually works, not just how we think it works, right? So this is how the world actually works. A centrifuge should actually be called a centripetal fuge. I don't know, that was a bad joke. But anyway, so now that we're clear on that, most textbooks will describe the centripetal force. They will use the notation FC, and they will say, oh, FC is a centripetal force. I hate that, and here's why. Here's why I hate that. There's no such thing as a centripetal force per se. And here's what I mean by that. Gravity is a force. There's objectively something that causes the force of gravity. Tension is a force. Tension is a force provided by a rope. Friction is a force. It is generated by the rubbing of two surfaces, right? Centripetal force is not a separate force all on its own. It is actually the result of many forces. It's actually equal to F net. So, you know, let's take the car example, for instance. I said, you know, when you're turning the corner and your body wants to go straight, but eventually, you know, the car pushes on your body, and then that push from the car is what makes your body turn the corner. It's really the push here. It's actually a normal force. It's a surface contact force. The surface of the side of the car is in contact with the side of your body. And it's the push from the surface that's actually pushing you around the corner. So in that case, the force responsible for that circular motion of your body in a car turning a corner is the normal force. So centripetal force is not a separate source of force like friction or tension or normal force, right? It is a resultant force. It is, you know, there are other more fundamental individual forces that are causing the circular motion. If I just scroll up here, for instance, if we looked at this, this ball on a string again that we looked at earlier, there would be a sort of centripetal force. There would be an inward force keeping this ball traveling in a circular trajectory. However, there is no source of centripetal force. In this specific case with the ball, the source of the force would be tension in the string. Now, if this point isn't clear at the moment, it will become clear later on in the lecture, I promise you, once we move forward. But I'm going to mention it now and then loop back to it later. Now, how do we modify our analysis now that we're doing circular motion compared to regular motion? And the answer is virtually unchanged, with the exception of acceleration is no longer linear. It is centripetal, it's circular. So what we do is we still start with a free body diagram, as we always do. Remember what I said yesterday, when you're doing forces questions, first things first, you always draw a free body diagram, always. And the second thing I said was you always do F net equals MA, always. That's still true. It's not like I'm reneging on that claim. So you draw a free body diagram, and you draw F net equals MA, just like before. And the only difference, though, is the acceleration is not linear anymore. The acceleration is centripetal or circular. So I like to just write F net equals MA, and then put a little subscript C beside the A to indicate or to remind myself that it's not linear acceleration, it's circular acceleration. But then I proceed with the analysis exactly the same as I would before. You know, I can sum all my forces from my free body diagram. I could do F net X, F net Y if I needed to. And then what I do is, you know, I can either solve for A as a variable, or if you need to solve for something a little bit more fundamental, like the speed of the object or the radius of the turn, you can actually represent A as V squared over R if you'd like, depending on what we're asking. So you could actually go off and say, you know, in the case of circular motion, F net equals MA, A could actually be represented as V squared over R. So you could actually say F net equals MV squared over R. But please understand, it's not a different equation, and it's not a different setup, and it's not a different approach. It's exactly the same approach as what I was saying yesterday. Start with a free body diagram, then go to F net equals MA. Okay, so here's a conceptual example. And normally I would do a polling for this, but I think just for the sake of time, we're just gonna go through it without a polling. So you revolve a ball around your head in a horizontal circle with a constant speed attached to a string as shown below. Which path would the ball follow if I just let go of the string? You see here I've let go of the string. And what path would the ball follow if I let go of the string when the ball was right here? So there's different options. There's A through G. A says the ball would just spontaneously go away from me without traveling left or right. It would just immediately stop moving forward somehow and just move away from me. I think we can all agree A is just not likely. You also have to remember there's an initial speed here, right? If I'm in the middle of turning a ball around over my head and I just randomly let go of the ball, at that moment in time, there is an instantaneous velocity traveling to the right. Okay, so if I let go of the string, that instantaneous velocity traveling to the right is not just going to magically disappear. So for it to move in the direction of A is just completely unheard of. And same G. G is like if I let go of the string, the ball comes at me. That makes no sense. Okay. B might be, you know, an understandable mistake. For people who think centrifugal force is an outward force, you'd say, okay, well, if there's something pushing the ball outwards and I let go of the string, then it will actually go to the right and a little bit outwards. So you might think B, or for that case, C. B and C look very similar. I guess the angles are just a little bit different. E and F, well, okay, F is obviously wrong. F just says if you let go of the string, the ball's going to continue on in a circle as if nothing's different. So obviously F is going to be wrong. So now we're down between D and E. So E says, you know, we're going to partially continue turning in the circle, but because I've let go of the string, there's nothing keeping it in the circle per se. So as time goes on, you know, it's just going to spread out. This is a nice thought, but in fact, you notice here that would violate the law of inertia. A body in motion wants to remain in motion. So if the initial, when I let go of the string, if the initial velocity is to the right, then the law of inertia says the velocity will continue going rightward toward the right unless there's a force that acts on the object. It won't naturally just spontaneously deviate from its velocity. Like you need a force to change that direction. So if I let go of a spinning object, it actually flies out. Let me draw this in blue. It actually just flies out tangent to the circle in a straight line. So it doesn't continue on an arc, or it doesn't continue on in an arc, even if it's a larger arc than the original circle. It just continues straight out. So that's the answer there, and there is the answer is D, and there's a bit of an explanation there. You can go back and read it later if you want. So I think we are now at a point where we can just jump in and do some problems. Let's see here. Yeah. So we're just going to do just bang, 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 bang. We're just going to do some examples of questions, like textbook examples of questions that have circular motion concepts that you need to analyze them. So that way you actually get to see how to solve these in practice. Even though I've really said all the theory, right? You just do free body diagram, F net equals ma, and A is represented by V squared over R. It's really no different. Now we can just jump to it. I'll literally show you what that means. So the model airplane in the figure below has a known mass of, okay, so physicists and words. Let me just start writing values down. Mass equals 0.9 kilograms, okay. At a constant speed on a circle. Okay, so it's a circle, so I know it's not linear motion, it's circular motion, okay. Parallel to the ground, so it's horizontal. The path of the airplane and its guideline lie in a horizontal plane. Okay, the question's already said horizontal because the weight of the plane is balanced by lift. Okay, those are all words I don't care about. Find the tension. Okay, so words confuse me. Find tension, so T equals question mark. In the guideline with length, okay, length equals 17 meters. For speeds, okay, more values. Speeds of 19 and 38 meters per second. Okay, and there's a little picture there. All right, so words are aside. My first read through of a question, and it always jumbles my brain. So, I know they're talking about something about an airplane around the circle over my head. If it's confusing, that's fine. You can give it a second read after you've parsed it and after you've written out all your values. So if you read it a second time, you no longer have to worry about any values because you've taken care of that. You can really focus on the setup of the problem. So reading it a second time, you notice that there's an object. There's an object that is in the middle of traveling in circular motion, and it's attached to a string, and the string is providing the tension. Now, that is the free body diagram. Now, they technically, if you want to get technical, I suppose, they mention that, let's not use blue, let's use green. They mention that there is gravity pulling down, but the force of gravity downwards is balanced by the lift of the wings. So those just cancel pretty much. So we don't necessarily need to worry about those. Now, here's what I was talking about earlier. There is no such thing as centripetal force. If centripetal force by itself was a separate force, it would show up on our free body diagram as a force. I'm not labeling FC as a force because FC itself is not a different force. Yesterday I said when you draw a free body diagram, you have to draw a free body diagram in such a way that you only draw forces that are physically touching and physically acting on the object. The only force physically acting on this airplane is tension. I guess, yes, gravity and lift, but those cancel. So that's what I draw. I don't magically label FC. I just label tension. And this is what I was saying before. Your analysis technique is no different now than it was before. So now, after drawing my free body diagram, I'm going to go through and I'm going to say, all right, let's start with my F net equals ma. If you really want to be super technical, yes, we've got two directions. We've got the y direction and the x direction. So I could say f net y equals may, and then I can say f net x equals max. F net y. Okay, well, looking at your free body diagram, I have the force of the lift upwards, and then downwards in the opposite direction, so minus, I have the force of gravity, equals m times the acceleration in the y direction. Well, presumably, you know, if this airplane is traveling in a horizontal circle, there is no movement upwards or downwards, right? The vertical position is constant. So the acceleration in the y direction is 0. And here you just see that the lift provided by the wings would be equal to the force of gravity, mg. It's valid, it's just not very useful in this case. That's why I was saying earlier, the lift and the gravity just cancel. Okay, so that's that. Moving on to the x direction. Okay, f net x. If you look at your free body diagram, and this is why it's important to have a free body diagram before you do f net equals ma, your eyes can just look how many forces are in the x direction. Only tension. So I would say just my tension force equals ma in the x direction. And previously to this, like with linear motion, we would just leave a as a. In fact, well, actually now let's just leave a as a. I'll show you kind of how to do this. So we know, do we know tension? No, we're solving for tension. So sorry, we can't leave a as a. We have to kind of replace it with something. So we do know that the acceleration isn't linear. We know that it's actually centripetal acceleration, MAC. So this allows us to actually replace our variable a in terms of other variables that we might know. So we know a is in fact v squared over r. And we're asked for tension, right? Tension equals question mark. Do we have all of these variables? M we have 0.9. V, I guess there's part A and part B, but V we have is 19 for part A and 38 for part B. And R, the radius of the circle. Well, the radius of the circle would be the length of the string. So yeah, I'd say we have everything. Now your final derived equation should be in terms of variables provided in a written question. So instead of leaving it as R, I'm just going to replace R with L for length. So there you go. That's the tension in the string to get a mass m moving at speed v with a radius of L in uniform circular motion. Okay. Obviously, A and B is fairly simple. A, you just make V19, and B, you make V38. Not a big deal. Just in terms of numbers, though, I want you to see something. 19 versus 38. That's a factor of 2, right? So V2 equals 2V1. However, if you double the speed, do you double the force? Well, with V1, you need 19 newtons. Let's call it 20. And for V2, you need 76 newtons. Let's call it 80. Well, that's a factor of 4. You double the speed, you quadruple the force. Well, that's because of V squared over R. The acceleration is proportional to the square of the velocity. So a doubling of speed would actually quadruple the acceleration and thus quadruple the required force. Let's keep going. So that's with a plane. Oh, I will say conclusion here, maybe in red. This is an example of how tension causes circular motion. Okay. Now, I've already mentioned this before. Cars. You know, cars turn corners all the time. So cars are something that we see in a day-to-day, in our day-to-day lives that will undergo uniform circular motion. So let's kind of analyze the physics of that. So how large must the the other thing, we've already established that the force responsible for carrying a car forward is friction. And if you're still not comfortable with that, I really encourage you to go back and not only review the type lecture notes, but do some practice problems. The only way to really become comfortable with that notion is seeing it done, you know, in an actual physics problem. So we know friction is the force responsible for making a car move forward. So friction is also the force responsible for pulling the car around the circle or around a corner. So how large must the coefficient of static friction be? Oh, so words confuse me, so let's just write that down. How large must the coefficient of static friction be between the tires and the road if a car is to turn a round level corner with a radius of 125 meters at a speed of 95 kilometers per hour. Okay, so again, it's a new situation. I as a student, I might feel a little bit nervous and confused and lost, but I'm going to remember what Mark said when you study forces problems. Step 1, free body diagram. Step 2, F net equals ma. So here's my free body diagram. Label the forces. Gravity is always a freebie. This car is sitting on a road. So if it's sitting on a road, there's going to be a normal force. And if the car is turning the corner here, then there's going to be a force responsible for pulling it around the corner. And the question even gives you a hint that this is going to be the force of friction, pointing radially inward to pull it around the corner. All right, so there's your free body diagram. Then we can move on to F net equals ma. And how many directions do we have? Well, I see 2 directions. So we need to do F net x equals max, and we have to do F net y equals may. All right, let's do x first because that's the one I happened to write first. So F net x, again, the whole point of a free body diagram is that all the forces are in an organized way for your eyes to see visually. Let's look at our free body diagram. In the x direction, the only thing I have is force of friction. So that's easy enough, force of friction. I'm not going to get fancy. I'm not going to write mu Fn yet. I'm just going to kind of keep it simple for now, one step at a time. Equals m and my acceleration in the x direction. Okay, so I've got to think about, is my car accelerating in the x direction? And looking at your free body diagram, the answer should be pretty clear that the answer is yes. There's only one force in the x direction, which means there has to be an acceleration in the x direction. The question is, what kind of acceleration is it? Is it just a traditional old, like a linear acceleration, or is it something different? And you can see from the diagram here in the picture, it's going to be something different. It's circular, right? The net force is radially inward, so the acceleration is radially inward, and it's part of circular trajectory or circular motion. So this acceleration, oh, that's weird. This acceleration is going to be centripetal. Force of friction equals ma, but it's not a normal a, it's centripetal a. So F net equals ma sub c. All right, so that's there. Now I can start expanding things. Okay, so force of friction. I know the force of friction is mu static Fn. M is m. AC. Okay, well, AC I know is going to be v squared over r. Do I have speed? Yes. Do I have r? Yes. Do I have normal force? No. Okay, so we have 2 unknowns and 1 equation. We've got mu and Fn, 2 unknowns, 1 equation. That means we need a second equation. Luckily, we have 2 dimensions. So if we go to the y direction, F net in the y direction, let's see here. Looking at my free body diagram, I have how many forces? I've got what? Two forces. So I've got normal force upwards minus gravitational force downwards equals, and this is going to be m And what's my acceleration in the y direction? Well, this car is sitting on a road, so the y direction would be like, you know, up or down. Is this car magically levitating or magically being driven into the ground? No. So you can tell from context that the acceleration in the y direction is going to be 0. So that means the normal force is going to just simply be the force of gravity. So plugging this in to that equation, we get mu, now Fn was mg, equals mv squared over r. And pulling out our math brain for a second, we can cancel the m's on both sides. And we get mu static is equal to v squared over rg. There you go. So what is the coefficient of friction required to pull this car around a corner? Well, it's going to be the square of the velocity divided by the radius times g. And the interesting conclusion here is that this is not a function of mass. I thought it was going to be, right? Because we had m's in our equation, right? But it turns out if you keep everything as a variable and you kind of go through with the calculation, m's kind of just drop out. So it turns out that the required frictional coefficient to pull something around the corner is not a function of the type of vehicle or the mass of the vehicle. In real life, what does this mean? It means that if you have an icy road, it doesn't matter whether you're a smart car, whether you're a regular car, or whether you're a transport truck. It doesn't matter how heavy or light your car is. An icy road is an icy road, and if you can't make it around the corner in your regular car, a transport truck won't be able to make it around a corner just because they're heavier, right? That's what this equation says, is the required coefficient of friction you need to turn a corner safely is not a function of mass, not a function of car. It's a function of, you know, the road conditions. So just, you know, if you're driving a bigger vehicle, like let's say you drive an SUV or a pickup truck, you know, don't think you're safer on the road because you're in a heavier vehicle, right? The physics explains that you're not. I should also say that this is an example of the force of friction causing circular motion. So we've seen tension cause circular motion. We've seen friction cause circular motion. There's the solution there. Let's keep going. We have another question. And also, this is what I'm saying when I say that the centripetal force itself is not a separate force, right? I've shown you an example how tension can cause circular motion. I've shown you an example of how friction can cause circular motion. Right? There is no such thing as a centripetal force per se, as a separate force. The centripetal force is actually the net force acting on an object that just so happens to cause circular motion. So here's another example of where normal force will cause circular motion. You know, it's the same scenario really when your car turns a corner and, you know, you follow your car. An amusement park ride consists of a large vertical cylinder that spins about its axis fast enough that any person inside is held up against the wall when the floor drops away, as shown in the figure. The coefficient of static friction between the person and the wall, right? You know, your back is touching the wall. Those are two surfaces that are in contact with one another. So, you know, a shirt is cotton, the wall is, I don't know, metal. There's going to inherently be a coefficient of friction between, let's say, cotton and metal. Here it's just going to be mu s. The radius of the ride is known to be capital R. Show that the maximum period of revolution that is necessary to keep the person from falling is that. That shouldn't say maximum, I think it should say minimum. Oh no, maximum? Yeah, well, whatever. Calculate the period necessary to prevent the person from falling. Obviously, if the floor drops out and you're not traveling fast enough, you'll just fall, right? The whole premise is this thing is traveling fast enough that if the floor drops out, you remain stuck, if you will, pushed against the back of the wall, and you will not fall down. So again, new situation, things are a little bit confusing. I'm going to read it again to list all the information that we're given. So let's see here. We're given, oh, I'm writing in red. We're given mu, we're given r, and we're asked to calculate t. So we're not given a whole lot. This seems complicated, this seems daunting, and I can completely understand if students are left feeling confused with how to approach this problem. However, fear not, listen to what I said yesterday. It's a forces question. Every single forces question is analyzed exactly the same way. Start with a free body diagram and then do F net equals ma. So let's start with the free body diagram. There is gravity pulling down on this person. Here the premise is the floor drops away. So if the floor drops away, there's no normal force upwards. Like normally when I'm standing on a floor, gravity's pulling me down and the floor is pushing me up, right? Normal force upwards. But if the floor drops away, there's no normal force. However, I am leaning against the wall. So if gravity's pulling me down, the tendency of motion would be downward and there would be slipping. So there would be a force of friction upwards. And the other thing is we are traveling in a circle, as you can see in the picture. And I know you can relate to this because your body has experienced this. You know, if you're traveling in a circle in a car, you know that the surface of this cylinder is going to be pushing your body radially inward to keep you going in a circle. So there's actually going to be, and this is really the trick of the question, there's actually going to be a normal force from the surface pushing on your back, not from the floor on your feet, from the wall pushing on your back radially inward toward the center of rotation. Okay, so there's my free body diagram. And then we do F net equals ma. So as before, we've got two directions. So let's do F net x equals ma in the x direction. Again, the whole point of drawing a free body diagram is you can just see it. How many forces are in the x direction? Just the normal force. And what kind of acceleration is occurring in the x direction? It's centripetal. It's not linear. It's not like this person is literally accelerating or literally moving radially inward, right? They're moving in a circular path. That's their trajectory. Their acceleration is radially inward, but their trajectory, it's not linear. They're not literally moving inward. They're moving in a circle. So it's not linear acceleration, it's centripetal acceleration because it's circular motion. And I can just expand that. mv squared over r equals the normal force. So in this case, it's the normal force that's responsible for causing this person's trajectory to be circular. It's the normal force that causes circular motion here. Okay, what do we have? We're asked for period. Okay, well, I don't even have period in my equation. So I need to introduce period somehow. Well, I do know that if an object travels in a circle, the distance traveled is the circumference, 2 pi r, and the time it takes to travel is called the period. So v is going to equal d over t, is going to be 2 pi r over the period. So there we go. This is going to be mass v squared. 2 squared is 4, pi squared is pi squared, r squared is r squared, over period squared r. Simplify a little bit here. And I'm going to get 4 pi squared rm over period squared. Okay. So what do I have? Well, we actually have nothing in here. Sorry, yeah, we have the radius. We have the radius. but that's all we have. We don't have mass, we're looking for the period, and we don't have normal force. Fear not, trust the physics. So don't panic. We've done F net X. Let's proceed. Oh, I'm still in red. I don't think there's any further we can do with the X direction. Normal force doesn't really have a known, there isn't one equation for normal force like there is friction, like mu Fn or anything. So we just have to like leave it as Fn. Moving on, F net in the Y direction is going to equal MA in the Y direction. And hopefully the goal of this problem is that this person does not accelerate downwards. I mean, if it was traveling too slow, yes, this person would fall downwards, but our goal is that they do not fall downwards. So we are trying to achieve a zero acceleration here. Looking at my free body diagram, what kind of forces do I have in the Y direction? Force of friction upwards and gravity downwards, okay? So mg upwards and mu Fn downwards, and this equals 0. It's mu static. I should really be more careful in my notation. So this actually tells me that the normal force is in fact equal to mg divided by mu s. So now we're getting interesting here. Okay, so here the normal force is mg over mu s equals 4 pi squared rm over period squared. Where does that leave us? Okay, well the m's cancel. That's good because we didn't have m, so I'm glad the m's cancel. We have r. Okay, and what do we ask for again? We're asked for t. We're asked for t. Okay, so let's solve for t and see kind of where we're at. So period squared is going to equal, let's see here, 4 pi squared r over mu s over g. And then if we take the square root of both sides, that should be our answer. Right there. Now, 4 and pi are constants. Do we have r? Yep, r is given. Mu, do we have mu? Yep, mu is given. And g is a constant. So there you go. That's our answer. We have all the variables in this formula are given in the question. So we're done. That is the required period of oscillation or the period of rotation that this amusement park ride needs to achieve in order for it to be safe, in order for the floor to drop out and no one gets hurt, no one falls out of the ride. So this is an example of normal force causing circular motion. There's the answer there. Okay, moving forward, moving right along. Here's another example of tension, but now it's sort of more ideal, or sorry, less ideal, more realistic. So, you know, if you're spinning something over your head, technically it's never going to be perfectly horizontal, right? Gravity is pulling it down. So this question says when you're spinning something in a circle, it's not going to be in a perfect horizontal loop. It's going to be sort of at some sort of inclination angle, theta. So the question here says, you know, a small object of mass m. Okay, so I'm going to write that down. We have m. Is suspended from a string of length L. Okay, we have L. It revolves with a constant speed. Okay, so we have speed. With rate, oh, we don't have speed. Okay, in radius r, and it says find the expression for speed in terms of everything else. Okay, so the airplane example we did earlier, we assumed that was a perfectly horizontal loop because gravity was counteracted by the lift of the wings, right? That's how airplanes work. The wings provide lift. In this case, the ball on a string does not have lift. There's no wings on a ball. So gravity will in fact pull it down, but eventually when it's down, there'll be a component of tension, as you see here. There'll be a component of tension pulling upwards to balance out gravity. And the angle at which, oh, I guess we also have theta. The angle at which the ball is going to take relative to either the horizontal or the vertical, depending how you want to measure it, is going to be governed by when the vertical component of tension perfectly cancels out gravity. Now, that may have been confusing for you. I sympathize. Again, keep calm, draw a free body diagram. You should be fine. So the free body diagram is sort of already drawn for you, but I'll draw it here again. We have the force of gravity, and we have tension. That's it. Don't be fooled. How many forces are acting on this ball? There's no surface, so there's no normal force. There's no rubbing, so there's no friction. There's gravity, and there's tension. That's it. Now, from here, we can assign a coordinate system. X, Y. And the picture has depicted that the angle that they're giving us, oh, let me just draw this in a different color, sorry. The angle that they're giving us is in reference to the vertical. They're giving us that angle there. That's fine. I mean, another question might give you a different angle. Who cares? I'm just gonna label what they give us and do grade 9 geometry based on what angle they give us. So there's my free body diagram. Staying calm and continuing, I'm just gonna do what Mark has been saying for the past like 3 days now. We need to, after this free body diagram, we gotta go back and do F net equals MA. So we're gonna have 2 F nets. Hopefully you're being, actually this is terrible for a teacher to say, I hope you're bored right now, because I hope you realize that what I'm doing is exactly the same thing every single time, between an airplane, between a car turning, between an amusement park ride, between a ball on a string. I hope you're bored, because I hope you realize this is all the same analysis, even with different types of questions. At the end of the day, it's all the same. That's the beauty, really. That's the beauty of Newton's laws, is any situation we can manufacture is, at the end of the day, really just the same. So I'll proceed to show you how to do this, but it's really the same as everything else. So F net in the x direction, I'm looking here, and I have a component. I have a component of my tension in the x direction. So that's going to be T in the x direction equals m, and the acceleration of this object, I mean, this object is traveling in a circle, so the acceleration is radially inward, so it's going to be a centripetal acceleration. Looking at my grade 9 geometry here, the x direction of tension is going to be what, the opposite side? Up, opposite side. So this is going to be T sine theta equals m. Do we have v? Yeah, we do. So I'll say v squared over r. And I don't really think there's anything further we can go with that. The y direction. Well, I have a y component of tension, and I've got gravity fighting that. And the acceleration in the y direction, presumably if I'm swinging a ball in a circle, it's not traveling upwards continuously or downwards continuously, like it's at a certain fixed altitude. So the acceleration in the y direction is going to be 0. And that tells me, looking at my geometry here, let's see here, the y component is the adjacent side. So this is going to be T cos theta equals mg, or T equals mg divided by cos theta. So going over here, do we need tension? What do we want? We want speed. Okay. So Tension, I can eliminate tension. Tension is going to be mg divided by cos theta multiplied by sine theta equals mv squared over r. Do we have m? Oh, we have m. Oh, look, we don't even need m. Look at that. That's cool. The m's cancel. So even though we're given m, we don't actually need m. That's kind of fun. Okay, so what's left here? We want speed. So v squared is going to equal, what is this? R times gravity. Sine over cos is tan. And I guess I can take the square root. So there you go. This means that the speed is going to be the square root of rg tan theta. Done. So if the ball was traveling slower than root rg tan theta, the ball would be traveling too slow to maintain circular motion, so it would start to fall. If the ball was traveling faster than root rg tan theta, then the upward force of tension would be stronger than gravity, and the ball would continue to rise. So I don't have a small cord with me. There's also stuff around me that I don't want to break. But an example of this would be, if you have a string and like a mass on the end of a string, as you rotate it, if you rotate it slowly, it might be down here. Like if I do this, I'm gonna hit myself in the face. If I do this, the string is kind of hanging low, right? It's hanging down here. But if I spin it really fast, in fact, you might even be able to hear the wind whistle. If I spin it really fast, instead of the string limping down here, the string, there's a larger tension than there is gravity, so the string increases the angle and becomes more horizontal to the point where the upward tension of gravity, the upward tension balances the downward pull of gravity. And it's only at that sweet spot that it's no longer going to move. So that's the speed at which we calculated. You could reverse this too. You could say for a certain speed, what angle will the ball take? So it really depends what variable we're asking for here is. So like, let's say my arm muscles have the ability to only make this thing travel at a certain speed. What could I do? What kind of angle could I achieve with that? All you have to do is just rearrange for theta. Okay. Oh, hold on. I'm not quite done. Sorry. We don't have R. Do we have R? A circle of radius R. Oh, but we have L. We have L. So L is what's given in the question. R, don't forget, R is this distance. We're actually given the hypotenuse. So, okay, again, it depends what you're given in the question. This is a valid equation, assuming you have the radius of motion. We are, in fact, we're told, I don't know why this doesn't work all the time. We're in fact only told we have the length. So this specific setup, maybe because, I don't know, our instruments are bad or something, we only know the length of the string. So we can actually say this is going to be what, sine? So sine theta equals opposite over hypotenuse. So we actually know that R is equal to L sine theta. So we can actually go back and we can plug this in. So V is going to equal to, instead of R, I'm going to write L. So this is going to be LG sine theta tan theta. Depends what they give you. If they give you R in the question, you don't need to do that extra substitution. If they give you the hypotenuse, like the length of the string, and not R, then you can go back and swap that out. Okay, so just to summarize, for horizontal loops, we have a few different scenarios I've shown you. We have a centripetal force or circular motion caused by ropes. you know, with the airplane question. Circular motion caused by friction with the car, circular motion caused by the normal force. You know, that could be like a body in the car, and the car pushes your body, you know, when you're turning the corner, or it could be when you're in like a roller coaster ride and it's spinning. And we have a sort of like a tetherball question, which we've just done, where the overall trajectory is a horizontal circle, right? This ball physically travels in a horizontal circle, but the point of origin is not at the center of the circle. It's either like above or below it. So there's a sort of angle involved there. Vertical loops, there really isn't a whole lot to vertical loops. Everything here we've done is a horizontal loop, right? Vertical loops are a little bit fun. Come on. But again, it's a new situation, so I can understand students being confused by it, but please understand at the end of the day, it's the same stuff, different situation. So here it says a pilot of mass M, okay, M equals check mark, is doing a loop-to-loop, so it's a vertical loop instead of a horizontal loop. The aircraft moves in a vertical circle. Here we're given the radius, check mark. At a constant speed, so we're given a speed, check mark. Determine the force exerted by the seat on the pilot, so determine the force of seat on pilot. That's a surface contact force, so that would be the normal force, equals question mark. Oh, at two locations, at the bottom of the loop as well as at the top of the loop. Okay, so let's say A is bottom. So, okay, at the bottom of the loop, which is down here, it's in the middle of going up. And we know that in circular motion, the centripetal acceleration is always pointing radially inward. So we know the acceleration at the bottom is pointing up. Now, acceleration is not a force, so we don't label acceleration in the free body diagram. I only label the forces. So gravity is pulling the pilot down. Now what's preventing the pilot from just falling out of the sky? The normal force from the seat on the pilot. I don't think there are any other forces. Inertia is carrying the pilot forward, but there is no force forward. There's only gravity down and normal force upwards. So this is easy. We only have one F-net equation to do, because there's no two dimensions, there's only one dimension. And what kind of acceleration is it? Well, it's centripetal acceleration. Net force, looking at my free body diagram, I have the normal force upwards and the gravity downwards equals mv squared over r. And here, the normal force is gonna equal mg plus mv squared over r. All right, here, this is gonna be m times g plus v squared over r. So there you go. The normal force, you can see here that the normal force that the pilot will feel is actually larger than his weight. So the normal force is actually larger than, well, I'll say W just to really hit it home, larger than the weight. Because here you see the normal force is his weight plus something, larger than his weight. So I'm sure you felt this on a roller coaster ride. At the, you know, let's say at the top of a hill, the roller coaster goes down, 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 and then right before it crashes into the ground, the roller coaster kind of pulls out of the nosedive and you know, starts going up. Now, as it's pulling out of the nosedive, the roller coaster is in the middle of going through uniform circular motion at the bottom of the vertical circle. And you know, if you're a particularly brave person, when you're on a roller coaster, you know, your hands are kind of up in the air, and then at the bottom, you feel heavier. And the reason you feel heavier is because the normal force is larger than your weight. And the fact that you feel heavier is actually a psychological thing. When you're moving your limbs and when you're walking around, your brain and your muscles they're used to the weight of what your body is normally. You know, like I weigh about 180 pounds. If I were to just put on 100 pounds, like in the snap of a finger, if I all of a sudden weighed 280 pounds, I probably wouldn't be able to move. Like my muscles are not used to moving that much mass. So pretty much at the bottom of a vertical loop, that's what's happening. At the bottom of a vertical loop, it simulates as if you weigh, you know, more than what you usually weigh. So your muscles and your brain are not used to moving that much mass. So, you know, you feel different. You feel like, oh, this is odd. It's a weird feeling for me. So that's what's happening at the bottom. Now for the top, we draw another free body diagram. Gravity is still pointing down, of course. But at the top of the loop-de-loop, you know, the velocity is carrying you forward, right? At the top of the loop-de-loop, the velocity is carrying you that way, yet you're not going that way, right? You're physically going to be, your acceleration is downwards. So at a moment later in time, you're going to go a little bit to the right and a little bit down. So a moment later, you're going to be over here and then over here and then over here. So at the top, your acceleration is downwards. So that means there has to be a force pulling you downwards. So at the top of the loop, the seat isn't pushing you up anymore. Don't forget, at the top of the loop, the seat is upside down, and you yourself are upside down. So the seat isn't pushing you up anymore. That doesn't make any sense. The seat is in fact pushing you down. And now that we have our free body diagram, we simply do F net equals ma again. And my net force here is normal force plus gravity equals ma. And here, my normal force is going to be m times, mac. So this is going to be v squared over r minus g. Just like that. And this here means your normal force is actually going to be less than, well, actually, we don't know. We don't know if it's going to be less than gravity. If you're going really, 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 really fast, hopefully it's safe and you're not going super, super fast. But, you know, if this thing is whipping in a circle like a centrifuge, then yeah, the normal force pulling you back in might very well be quite a bit larger than your weight. Now, it could easily be smaller than your weight as well, though. But it would be incorrect for me to say that it's always less than your weight. It's the magnitude of the normal force at the top is whatever it needs to be to keep you traveling in that circle. Sometimes it'll be larger than the weight. Sometimes it'll be less than the weight. So here's a little pictorial example here. At the bottom, the normal force is really large, which is why you feel heavy. And at the top, assuming we're traveling at a constant speed, I guess you can guarantee that the normal force at the top is smaller than what it would be compared to what it would be at the bottom. But we still can't guarantee it's going to necessarily be less than your weight. Okay, so we're pretty much done uniform circular motion, sort of. There's a small caveat that we have to do later, but just a brief summary here. You know, uniform circular motion, you got to remember, it's a constant speed everywhere. The velocity vector keeps changing direction, but the magnitude of the velocity vector is constant everywhere. The net acceleration, and I guess subsequently the net force that the object experiences is always going to be pointing radially inward. Nothing really changes. F net is really the same. It's still F net equals ma. The only difference is it's a sub c. It's centripetal acceleration instead of linear acceleration. So you can swap out a for v squared over r. But everything else, I'm sure you've seen it previously, is the same type of analysis as before. It's free body diagram, F net equals ma. Okay, this brings us to our last topic in circular motion. It's banked curves. And this is actually, a lot of students find this difficult, and I'm not sure why. It's really not that much different. It's still free body diagram, F net equals ma. But really what a banked curve is, we saw an example of on a horizontal road, a car turning. We saw that the only force responsible for it turning the corner was friction. And, you know, if it's icy or, you know, let's say you're going too fast, you know, maybe the amount of force required to pull it around the corner would be larger than the maximum static friction. So really all a banked curve is saying if the road is itself on a bit of an angle, theta, like NASCAR, I don't know if anyone watches NASCAR here, but if the road itself is on a bit of an angle, then you have two forces that are helping you turn the corner, friction as well as the normal force. And if that's not totally apparent at the moment, I'm about to show you why. Also, side note, this hamster, you know, in this caption here, totally me, 100% me. Actually, frankly, everything I do, I think of and I picture free body diagrams. But anyway, so here's a free body diagram of a typical car traveling on a banked curve. So like I said, instead of a flat horizontal road here, it's the same road, it's just kind of tilted up on an angle. So if you look at the free body diagram, there's only two forces, and I cannot stress this enough, only two forces. Well, actually, there might be three forces, but there's two definite forces. There's the force of gravity downward, and there's the normal force, which is pointing upward, that is perpendicular to the surface of the road. Now, circular banked curves, though, the car is still traveling in circular motion. The car is not traveling up the ramp, and the car is not traveling down the ramp, right? The car, it's like the tether ball. You know, there's an angle in the tension, but the tether ball itself, the result of the tether ball is just a perfectly horizontal loop. So, you know, even though this road is on an angle, the trajectory is still a horizontal loop. So the trajectory is uniform circular motion with a horizontal loop, and we know that the acceleration for uniform circular motion on a horizontal loop, we know the acceleration is going to be radially inward. So the acceleration is not up the ramp, the acceleration isn't down the ramp, the acceleration is horizontal in the x direction. If you're traveling too fast or too slow, you might end up with some friction keeping you up or pushing you down. So let's do actually an example, and we'll see kind of what this means. So here, let me just insert some space. Let me just insert a lot of space because we will need. Come on. There we go. Okay. So let's do some thought experiments. I think I'm still on green. Thought experiment. So with some thought experiments, if we're traveling too slow on this banked curve, let's take the extreme. Not only am I traveling too slow, let's say I'm traveling at like 1 centimeter a second, something ridiculously slow. If I'm traveling forward on this hill, on this bank, forward at like, you know, 1 centimeter a second, you know, you can picture yourself even walking on a hill. What's going to happen is, if speed is slow, object will want to fall down the hill. So if I were to draw my banked curve, if I'm traveling too slow, I will want to fall down the hill. Now, presumably, if I don't slide down the hill, presumably what keeps me on the hill is the force of friction. So if I'm traveling too slow, if I'm traveling too slow, there's going to be friction up the ramp, trying to keep me up on the ramp. A second thought experiment, if the speed is too fast, then the object will want to, I'm going to use this in quotes, flare outwards up off of the ramp. So if the object's traveling too fast, like let's say like 200 kilometers an hour around a corner, what's going to happen is the car doesn't want to turn that corner, so the car is going to slide. The car is going to want to slide, slide up off the ramp. Now, again, if you're traveling too fast, it will, in fact, slide off the ramp. And if you watch NASCAR, that happens all the time. But if you're only traveling just a little bit too fast, then friction is going to be acting down the ramp because that opposes the attempted motion. Attempted motion is up off the ramp, so oppose up off is down. So if you're traveling too fast, then you're going to get friction down the ramp. And if you want to remember calculus for a second, with the intermediate value theorem, we have one option or one scenario where if we're traveling the speed is too slow and the friction's up the ramp, and another situation where speed is too fast and friction is down the ramp. There has to be a situation in which we have a perfect speed where there is no friction at all. So here I'll say if speed is too small, force of friction is up the ramp. If speed is too large, force of friction is down the ramp. Therefore, there must be a speed at which there is no friction. And we know this, I mean, if you want to get technical, we know this because of the intermediate value theorem. Now, let's actually go ahead and solve for that. Oops. I can't write today. So let's go ahead and solve for this optimal speed. Now, as a side note, before we solve, if you've ever driven in and around the highways, the on and off ramps of a highway are an example of a banked curve. It's, it's a light banking, it's a gentle banking, but, it's not just a horizontal turn, as if you're turning right onto a side street. It's a nice gradual curve, and the road itself is actually tilted inward. So a banked curve that you experience on a semi day-to-day frequency is the on and off ramps of a highway. And you might notice, hopefully you notice if you're driving, hopefully you watch signs that are around you. When you're on the on and off ramp of a highway, you notice speed limit signs posted in yellow. Now, legally, a yellow speed limit sign is not legally binding. Meaning if a cop saw you traveling faster than 60 kilometers per hour, they cannot give you a ticket. It's not a legal speed limit. Yellow means suggested. We suggest that you travel at the speed. Now, here's the question though. Where does 60 come from? I don't know about you, but when I drive onto the highway, I never travel 60 kilometers an hour. Like I'm always doing like 80 or 100 to match the speed of the traffic on the highway. So like why are they, you know, they know this, like they know people drive faster than 60. So, you know, why are they patronizing us? Why do they post 60 to begin with? So I'm actually going to show you where that number comes from. It's physics. Well, engineers would need to know this, but I mean, it's just basic physics that we've now learned enough that we can solve for that number. I'll give you a bit of a foreshadow. The number 60 kilometers per hour is in fact the speed we're looking for. 60 kilometers per hour is the optimal speed that you need to drive so that you do not need friction to help you around the corner. And this is optimal because, you know, if the weather conditions are bad in Southern Ontario, our winters are pretty brutal, you know, we got black ice. Sometimes you can't necessarily depend on friction to turn your wheels or to brake or to accelerate or to turn, you know, stuff like that. So that number is there as a safety thing. If you're driving and you're not necessarily confident that, you know, you have the friction on the road, like let's say it's snowy and icy, and you're like, oh, I don't really know if my wheels are going to skid. That number is there for safety. It says if you enter the curve at 60 kilometers per hour, it could be a completely frictionless surface and you'd still make it around the curve safely. And if you go anything faster or slower than 60, you might crash if the weather conditions are bad. So that's where that number comes from. But let's go ahead and quickly calculate the set of optimal parameters for this. And in fact, we've actually already sort of seen the formula in an earlier question, which is kind of fun. So here, our goal is to relate optimal speed to other parameters. Optimal meaning no friction. So if I draw my free body diagram, I'm on a bank with a certain angle. Now, I agree, if you're going too fast, if you're going too slow, there might be a scenario in which you do have friction, in which case it's not really a different analysis, it's just something that pops up in your free body diagram and you just kind of include it in a term in your F net equals ma. But in our case, our specific goal is to not have friction. So I'm going to label all my forces, but not label friction, because that's our goal, is to not have friction. I always have gravity pointing downwards. I'm on a surface, which means there's going to be a normal force, and the direction of the normal force is pointing perpendicular to the surface. Now here's the caveat. This isn't just a ramp question. Like we did ramps, I think, yesterday. This is not a ramp. The object is not sliding up or down the ramp. The object is, in fact, traveling in a circle. So I know that the acceleration is actually pointing radially inward. So it's circular motion. That's what makes this different than just a regular ramp. Like I think we did a penguin on a ramp, I think it was yesterday. It's different than that because the penguin is actually sliding up and down in a linear fashion. This is not sliding up and down. This is physically traveling in a horizontal circle. So that's what makes this different. Now, there's my free body diagram. Then I just simply jump to F net x equals, oh, sorry, I have to say, before I do x and y, I need to make a coordinate system. Now, with the penguin, we did a rotated coordinate system. Do we do a rotated coordinate system here? And it's very tempting, very, very, very tempting to say, yes, we do a rotated coordinate system. However, I'll give you a trick. I'll give you a hint, which is a trick. You always want to line up one of your axes to be in the direction of the net force. And you might be saying, well, how do I know what the net force is? You know, it's not listed in the question. Well, you know the net force, F net, is equal to ma. Well, we know where a is. So the vector of F net is going to point in the same direction as the vector of a. And a points horizontally, radially inward. So the net force is going to point horizontally, radially inward. So that tells me I should probably make one of my axes horizontal. And my other one, because of independence, I have to make my other one perpendicular to horizontal, which would be vertical. So there's my coordinate system. And then I jump to F net x equals MA, F net y equals MAY, MAX. So same as before. Okay, so now I just look. F net in the x direction. I'm going to have, looking at my x direction, gravity is 100% in the y direction, so there's no component of gravity in the x direction. I do have a component of the normal force, though, in the x direction. So where's my angle? Let's see here. Boom, boom, boom. So that's my Z rule, which makes this theta, which makes this theta, which makes this theta, I believe. So my x direction, that would be Fn sine theta, right? This would be opposite, equals m, and my acceleration in the x direction is centripetal, so v squared over r. All right, I can't go any further. Fn is not really a force that has a formula, so we've gone as far as we can. Let's look at the y direction now. So the y direction, what forces do I have in my y direction? I have the vertical component of the normal force, so Fny, and I have 100% of gravity. Gravity is completely parallel to the negative y-axis, and this equals m times, and the acceleration in the y direction, well, the y direction is literally up, down. Is this car magically levitating off of the ground? No, obviously. The car is not accelerating up or down for that matter. So the acceleration of the y direction is 0. That's a terrible 0. 0. Okay, geometry. Fny is going to be the adjacent, ADJ, not ADY. ADJ. So this is going to be cos, right? So Fn cos theta equals mg. So the normal force is going to be mg over cos theta. All right, so now I know what Fn is. Beautiful. And I can plug this into there. So I'm going to get mg over cos theta times sine theta equals v squared, or mv squared over r. And then as before, we can cancel the m's and we simplify. Let's see what we get here. V squared is going to equal, let's see here, rg tan theta square root. So there you go. And we've seen this equation previously with the tether ball, because it's a very similar, in fact, it's an analogous situation to the tether ball. Here, the banked curve, the whole point of a banked curve is that it makes the normal force kind of up on an angle. And with the tether ball, the tension was up on an angle. So it's really the same situation. It's just a different mechanism for providing the force. So here's the optimal speed. Right there. This is where that 60 kilometers per hour comes from, is that optimal speed. And it's root rg tan theta. If you're traveling faster than root rg tan theta, which in real life a lot of people do travel faster than 60 kilometers per hour on those on-ramps. If you're traveling faster than root rg tan theta, there's going to be friction down the ramp. So that's how you know whether or not to include friction in your free body diagram. First, you have to check, calculate, what is my optimal or my critical velocity. And if the velocity in a question is larger than root rg tan theta, you know you're going to get friction down the ramp. Or if you check the velocity in the question against your optimal velocity and it's less than your optimal velocity, you're going to get friction up the ramp in your free body diagram. And you know, adding friction, it marginally makes your analysis a little bit more complicated, but really ultimately it adds a vector in your free body diagram, and it adds a component in the x direction and it adds a component in the y direction. It really doesn't make the analysis any more confusing, really, honestly. All right, that's pretty much it for circular motion. I'm going to stop the recording here temporarily, and I know we only have 3 minutes left, but we have another chapter, gravitation. I won't take long. We will go over time a little bit. I apologize, but we need to finish this this topic now. But I will make it a separate video. So I'm going to stop the recording now, and I will see you momentarily for gravitation.